Hey, so class, I'm going to go over how to do some of these problems in 6.4 if you're going to use a spreadsheet for your technology. So when we're doing these problems and we see normally distributed and we see find a probability, okay, if you recall, that means we're going to use norm dist or norm.dist. And we give it a number, we give it a mean, a standard deviation, cumulative, and that'll find the probability that it's below that number, okay? So if it says find the probability of individual distance is greater than, recall that means we're going to have to do 1 minus, okay, because it's going to give me below. If I want to do above, I need to do 1 minus the percent that's below. So 1 minus normal dist, the value that they're giving me here is 208.4. The mean is given right here is 195. The standard deviation is 8.9, and it says cumulative is the next. Remember, we do 1 for true when we're finding probabilities. So there's my answer. Again, they want this to 4 decimal places. I can click this button and have it go down and show me only 4 decimal places. So there it is to 4 decimal places. All right, now read carefully the next question. It's no longer asking what the first one is. Find the probability of individual distance. This is the overhead reach of distances. That's what's distributed normally like this. And that's what we're finding the probability of in the original. But that problem would have been fine in the 6.2 homework set. But this question, we're not finding the probability of a distance. We're finding the probability of a mean. So when we see that wording, it's still the same thing, meaning that we're going to do norm dist, and I'm still going to put in the number that they give me. It says greater than, so again I'm going to have to do 1 minus. And I'm still going to put in that number that they give me, the 193.2. I'm still going to give it the same mean. The mean is 195, but the standard deviation is what changes when we do these problems. The standard deviations for the distribution of sample means, and that's what we got here, a mean, is the old standard deviation, this 8.9, but I divide by the square root, SQRT for square root, of the sample size. The sample size is 20, so I'm going to put that underneath in the denominator. All right, close that off for the normal distribution as well, and there's our, I didn't give it the cumulative, sorry, comma, and then 1 for cumulative. All right, same thing, round it to 4 places, so I'm going to click back until I get to 4 decimal places. So there's my probability. When we are finding a probability of a mean, a sample mean falls in a certain range. That's a completely different distribution, and we now have to make sure we do that division by the square root of the sample size. All right, that's the central limit theorem. It's part of what we talked about in our lab, and we saw in our lab that magic number was 30. This question is asking, why do we not have to worry about the sample size being 30? And because it's the overhead reach of adult females is normally distributed. So we're normally distributed to begin with. The distribution of sample means will be normally distributed for even small samples, samples of size less than 30. So that's the one we're looking for. The normal distribution can be used because the original population had a normal distribution. So if we start off with a bell curve, the distribution of sample means is a bell curve. What we saw in that lab, though, is when we start off skewed, it took a while to become a bell curve, where we can actually say those histograms look bell-shaped. But 30 still is our magic number if it starts off skewed. This one didn't. So we started off with a bell curve. We ended up with samples immediately, even size 20 like this, have a bell-shaped distribution.